Hi everyone. Let's say that instead of population data, we have to rely on sample data, such as the results from a survey. Well, if we have sample data of size little n, we can calculate a sample mean, x bar, and from that, we can calculate a sample standard deviation, s, and a sample variance, s squared. In fact, we're going to calculate the sample variance first, just as we calculated the population variance first last time. Now, we want the sample variance to estimate the population variance of the population from which the sample was drawn. So ultimately, we might care about the population variance up here. But we can't get that exactly because we don't have the full census. We don't have the full population data set. So instead, we may have to draw a sample and rely on the sample variance. But again, the purpose of the sample variance is to estimate the population variance. We don't care about s squared in and of itself. We may only care about it in the sense that it helps us estimate sigma squared, the population variance. The same for s and sigma. So here's the formula for sample variance. And the standard deviation, again, is the square root of the variance. You'll notice that it's different. I'm going to go back to the formulas for population variance and standard deviation over here. So compare these two. Population variance over here, sample variance over here. Actually, I should reverse the colors. Oh no, this is fine. Blue here, red here. Okay. So many of the differences are in notation, right? Instead of sigma squared, the population variance, we're finding s squared, a sample variance. Instead of a population mean mu as our center, we're going to use the sample mean x bar as our center. Instead of population size capital N, we're dealing with sample size little n. So everything I've said so far has involved a difference in notation based on the fact that we're talking about sample data versus population data. But there is one computational difference. Here, for sigma squared, the population variance, we're dividing by capital N, the population size. Here, for sample variance, we're dividing by not the sample size, little n, but little n minus 1. There is a bit of a technicality here. So why is that? Why do we divide by n minus 1 here in the s squared formula? Well, here's the reason. Remember that we're supposed to plant our flag for the data set at the population mean. But here, when we're analyzing sample data, we don't have the population mean available to us. We just have a sample mean. The problem is that the sample mean is often an imperfect estimate for the population mean. There's some variability that's thrown in. The fact that we're using the sample mean, x bar, as opposed to the population mean, mu, that throws in a wrench, that throws in some more variability, which means that in order to better accomplish the goal of estimating sigma squared, and that is the goal of s squared, the goal of s squared is to estimate sigma squared, the population variance. Okay. But because of that whole x bar versus mu issue, we have to inflate the fraction a bit. Folks, let's say you have a third of a pizza versus a fourth of a pizza. Which is more pizza, which is less pizza? We have two fractions, the tops are the same. The 1/4, however, is less pizza because the denominator is bigger. The 1/3 is more pizza because the denominator is smaller. So when you go from 1/4 to 1/3, okay, then you're actually growing the pizza. So by dividing by n minus 1, we're actually inflating the estimate for sigma squared because of this wrench. All right, and again, s is the square root of s squared. We throw in the radical. All right. So I call this kind of a tilted average of the square deviations, the sample variance. It's inflated. All right. So let's say that this is sample data. There are 1,000 students in the class, a large lecture class. My TA, Igor, at the end of the exam, throws the 1,000 exams in the air and randomly grabs 5. By the way, what would be the problem with Igor just grabbing the first 5 exams off the top of the stack? Well, there could be some bias there, right? The last students who turn in the exam. Now, we don't know if they're the more conscientious students or the students who really needed the time, but there could be some biasing from doing that. So let's say that Igor randomly grabs the 5 tests from the air. All right. This is our sample, our simple random sample. These are our 5 sample data points. Now, the calculations are very similar. We have these 5 x values. The sample mean is obtained by adding the 5 scores and dividing by 5, 87.8 points. Again, these are the same 5 numbers as before for population data. We subtract off the sample mean, but again, we're dealing with the same numbers here. We get the same deviations, and they still add up to 0. We square these deviations, and we get the same values over here. So everything in these 3 columns is exactly like what we saw for the population data set, except we're using different notations. We're using x bar instead of mu. Now, to get the sample variance, what do we do with these square deviations? We take a tilted or inflated average. We add these up and we divide by, not by 5. To get the sample variance, we don't divide by 5, we divide by 4, n minus 1. The sample size minus 1. And we get 130.2 square points. The square root of that is about 11.4 points, the regular unit. All right. On a calculator, you might see an S, or this weird symbol, sigma sub n minus 1. I think S is a better symbol, but that calculates sample standard deviation if you input data. On Excel, all right, to find the sample standard deviation of this data set equals stdev dot s, sample standard deviation for this column. We get about 11.4 points, okay, as we got over here, right? And then for the variance, we just square that or work out equals var dot s for this column, and we get 130.2 square points. Again, like what we saw over here. Well, now, so what? So what that the sample standard deviation is 11.4 points? What can that tell us about the class of 1,000 students overall? We'll talk about applications and interpretations of standard deviation next time.